In this video, we're going to see how to analyze imbalanced data using cost-sensitive scoring with RapidMiner Auto Model. We're going to work on the bank marketing data set, which has customers of which 9% said yes to the banking offer and 91% said no. So with a 9 to 91% split, that's a fairly imbalanced data set, which could be challenging with some other techniques, but we'll see how RapidMiner Auto Model can help us to handle this. So the challenge here is that we're dealing with imbalanced data, and one other approach to dealing with this is cost-sensitive scoring. And what this does is that it assigns numeric benefits for correct predictions, penalties. So in other words, it assigns that if you get it right, you get bonus points, and if you get it wrong, you get malus points or negative points. And so the model, instead of just trying to get certain numbers or percentages correct or not, counts them as points. And so the models try to maximize the gain in bonus points and minimize the costs. So these gains might be in euros or not, or in some meaningful count. RapidMiner primarily uses an algorithm called MetaCost, which was the original cost-sensitive scoring algorithm, I believe. And now one thing to note, and this is very important to understand about cost-sensitive scoring, is that it works best if there are natural measurable costs, such as financial costs. So you should never use this technique when you're just making up numbers. For instance, if you're looking at cancer patients, and so which treatment should you use? Well, how do you quantify the cost of if the patient survives, or versus if the patient, well, they really didn't need that technique, and then but you applied it to them, well, that's a negative cost. You're trying to put numbers to things that don't have natural amounts. Like, what is the value of human health? What's the value of a human life? Or even if you inconvenience someone, how do you put a euro amount to that? Don't make up numbers. Cost-sensitive scoring does not work well there. In such cases, it's better to just balance the data or to adjust the thresholds. There need to be real meaningful numbers, otherwise meta-cost results would just be nonsense. And even for financial decisions, you have to be careful, because you should not think that all kinds of value can be converted into money. So for instance, if you're trying to predict how many customers will say yes, and so you're trying to minimize how many people you have to call because there's a cost of making calls. But when you call people, even if they end up saying no to this offer, they might say yes to another offer. Or they might think that, well, my bank actually cares for me, and they might become more loyal, even if they don't take that particular offer. And these things are not quantified in that particular campaign. So you have to be very careful from the wrong kind of thinking that everything that is valuable can be converted into money. So we're going to begin by importing data into RapidMiner. So for this, you need a premium version of RapidMiner that includes Auto Model, premium version or an educational version, but the free version does not include Auto Model. However, if you subscribe to Auto Model Go, to RapidMiner Go, which is relatively affordable, you should be able to follow these procedures. So let's click on Auto Model and to go in there, and you want to import data. You have the data on your computer. The data set we're using is bank marketing data set, so bank marketing. And this interface is similar to the read Excel operator in standard RapidMiner Studio. And we can accept all the defaults. However, we need to save the data. So I'm going to save the data in this folder here, because you have to save it within the RapidMiner repository in order to work with it in Auto Model. So the steps I'm going through are in the slides here, where you import the data. Then next we select a prediction task because we want to predict subscribed. That is, do the customers subscribe to the term deposit offer? Yes or no? Then click next. So to set up cost-sensitive scoring, we have this screen here in RapidMiner, and we're in the prepare target stage in Auto Model. And what we want to click is define costs or benefits. I'll make this a little smaller here so that we can focus on what we're doing. But let me explain how we're going to set this up. So one thing to make sure is that the class of highest interest is what we want here. And so yes, that means that customers who say yes, that's what we care about more. Usually the minority class, that's one that's smaller. In this case, 9% of customers is a class of highest interest, a positive class. So we want to make sure we have that. Then to set up this matrix, here's how I calculated these numbers. So our scenario is that the bank is contacting customers and is going to contact them by telephone in order to pitch this offer. So the cost of contacting a customer by telephone, let's say on average, is €5. That's how much it costs. And in other words, if the bank doesn't call the customer, then it costs them nothing. But if they call them, it costs them €5. So that's a negative cost. Then on average, if a customer is contacted and they say yes to the offer, the bank expects eventual revenues of €50 net, okay, not including this cost of contacting them. So those are the base numbers. So for cost-sensitive scoring, you have to calculate the numbers that apply in your organizational context. Now, based on these two key numbers, the costs in the cost matrix here are calculated as true positives. That means the model predicts that someone said yes, whereas they actually in real life did say yes. Then in that case, the profit is 50 minus €5 because the bank gets €50 from the customer, but there's a €5 cost for calling them. And so the net profit is €45. Now for true negatives, that is when the customer would have said no and the model predicted that they would say no, then the bank basically saved money by not calling them. Because the bank did not call them, they saved €5 relative to calling everyone. But because the model said this person is not going to say no, is not going to say yes anyway, the bank saved their €5 that they did not waste by calling everyone. However, for false positives are when the model predicted that someone would say yes, then the bank called them, but they ended up saying no. So this is money wasted. The bank spent €5, but gained nothing in return, so that's minus €5. But then a false negative is when the model predicts that the person would say no, but if the bank had called that person, the person would have actually said yes. So in that case, the bank saved €5 because they did not call the person, but they lost €50 that they would have gained. So that is minus €45. And these are the amounts that are calculated for each of these segments. And these are the numbers that need to be filled in like this. So we can go ahead in RapidMiner and fill in the numbers accordingly, just as has been explained. So this is 5. And here is minus 45. Minus 5. And here is 45. Okay. So that's how those numbers are calculated. And again, this is why it's very important for there to be a real, usually financial meaning, because otherwise you're just putting in nonsense numbers there. There has to be this careful calculation to compose a cost matrix. So once that is done, we can go ahead and click next. So the next screen, in the next screen, Auto Model suggests which columns could be used. Now, it's a good idea to click this I button. Probably should have done that from the beginning, but this is information which explains the documentation for every single field. So it's a good idea to keep this open while you're using Auto Model that explains what's going on. So here, Auto Model recommends that we keep these ones in green. The ones in yellow is not sure, but this is actually a very clean data set. And so we'll leave everything selected. Sometimes it has columns with the red that recommends to deselect, and you can read the reasons why, but that's not the case for a clean data set. So we go on now to model types. Now, in selecting the different kinds of models, let me close this so I can have a little bit more space here. You can see more of what's going on here. So RapidMiner Auto Model will run all these models and optimize them. It sometimes gives some options of what optimizations should be done. Others it will do automatically. And here on the right, it has some other data preparation things can do. It might offer automatic feature selection, including automated feature generation. So that is feature engineering. However, it gives this warning: automatic feature engineering creates and validates hundreds of thousands of models, which will increase the modeling time. And so let's skip that here. Actually, later I'll show you the results when I did run it with these features. Another thing that we'll deselect here is support vector machines. I'll just do that because I know that I've already run this, and it's the support vector machines is very slow, and it's not always that useful. In some cases, it works very well, especially when there's a graphical component in what you're trying to analyze, but a lot of times it's not helpful at all, which I know in advance is in this case. So here we'll just keep all the other models selected. We'll leave the others as default. Just make sure that that's what we have here, and we will run. Okay. So now this is going to take a while. And so I'll go ahead and fast forward here so that we can see the results of the run. So here we have the results for analysis. Now, people differ in what measures they prefer. Of all these measures listed here, the one that I found really useful is AUC. So I'm going to look at the AUC results. So here by AUC, we see here that the gradient boosted trees gave the best results in this case. And we have other good results. However, we are also very interested in the gains. So I'm going to sort by the gains. That's not a filter item there, but something that we can sort by. And we see that the naive Bayes model had the best gains. So that's basically 3,060 euros was the profit that it was able to make by its predictions. And it's not necessarily the one that had the best AUC that gives the best gains in the model. So let's look at these results a little bit more. We can compare the slides to see what we have. So first we'll look at So this is the overview. That's what we've been looking at. That's a default view. But let's look at the ROC comparison. So basically the area under the curve of the ROC. And this is what compares AUCs. Generally looking at this, you can see that this green line looks like the best one, and that would be the one corresponding to the gradient boosted trees. And we see that this yellow one is also quite good, and that's the one that would correspond, I believe, to the fast large margin. And when we look in the overview, we can see by AUC that indeed these are the ones that had good high AUC values. The naive Bayes is not necessarily the best, but it's a good contender, especially on this lower end. So other things to look at, a basic thing is the performance of the models, the standard performance statistics. And here we can see from the confusion matrix, you can see that the recall, which is this, so this is, the recall is the percentage of those who said yes, the percent of those who actually said yes were predicted yes. That's 64%. And you have other good statistics there. You can, in the overview, you can also quickly look by the recall, and that's often something that we want to look at. Here we see the fast large margin had 100%, and gradient boosted trees 100% recall. But whenever there's 100% performance, you should always be suspicious of that. So let's look at what's causing how fast large margin, for instance, got 100% recall. Fast large margin, by the way, is a variation of support vector machines. So when we look at its performance with 100% recall, well, that becomes obvious. It predicted that everyone said yes and no one said no. And so that's kind of cheating. So that's really not a very useful prediction. And so that doesn't help us much in distinguishing who actually said yes or no. And we can see that's why when we look at actual gains, the fast large margin had quite a bit of a loss because it sends out, it calls everyone, and so it lost a lot of money because most of them said no. So that's not a very helpful strategy to go by. So we can, by comparing, we can look at the performance even of the good ones. So gradient boosted tree also similarly had the same thing. Everyone predicted yes, and so inflated scores for recall, and so really not useful from that perspective. We can also look at the lift charts. So comparing the lift charts, and what I like to do with lift charts to compare them are, let's see, so that's lift chart. I like to go back and forth. I like to compare lift chart for naive Bayes, which was one of our best models, with generalized linear models. And when you click from one to another, you can see that the one on the top, naive Bayes, has a more concave outward shape, which basically means it captures more people faster. That is, it gives better bang for the buck. With the first 10% of people contacted, 36% of them said yes. It has captured 41% of those who in total eventually said yes. The next 20%, it was able to raise that to 56%. The next 10% was able to raise that to 66%, whereas the lift chart of those that were not as good did not capture as many people as you went on. So not as good bang for the buck. And that's kind of how I visually compare lift charts. So, so that's another tool. So even looking at the lift charts, comparing that for naive Bayes looks better than that of the fast large margin. Because unfortunately, there's not a tool here to compare them side by side, but by clicking back and forth, you can get the idea that the naive Bayes lift chart gives you more bang for the buck right from the beginning. So really, another thing to look at, trying to understand what. So this is the overall performance of the model. But if you're trying to understand from a managerial interpretation side, what aspects, what things actually mattered that made people more likely to say yes, then the weights are very helpful there. And this says here the campaign variable in that data set is that it basically tells us how many times a particular customer was contacted in this current marketing campaign. And so here is telling us that that is what mattered the most. The more a person was contacted, indicated more likely they would say yes. Then the next importance here, number employed. So it actually does not depend on the bank. It's the number of people employed in the Portuguese economy at the time the offer was made. This is a Portuguese bank, by the way. And so, in other words, the general employment rate of the economy, and that's also related to employment variation rate. That's so basically when employment was doing better in the economy, then people were more likely to say yes. Then other things are economic variables like consumer confidence index, the Euribor 3M, that's the interest rates. So a lot of things that determine if people said yes or no to this offer did not depend directly on the bank. However, the thing that mattered the most did. That was how often they were contacting the campaign. And so this gives some managerial insight on what they can control and what they might not be able to control. But the bank can still react to this. They can know that when employment is doing, when economic employment is not doing so well, that's not a good time to do a campaign. They wait until the employment is doing better, and that's when they launch their campaign. So even if it's not under their direct control, the managers can still act on it. Okay. So another useful tool here is the simulator. That is here, the using an auto model, they can estimate that if a customer who is, say, 52 years old, who was contacted, let's say we contacted them, well, let's move that. Okay, we contact them only 2 times. And here are the current settings in the economy. We contacted them using their landline telephone on a Thursday. They've never defaulted on a loan. Their highest education is high school. And here's the employment variable. So they basically set all these things for a specific case and so on. Let's say this person is divorced. Then what is their likelihood to say yes or no? And this then gives a prediction and said they are most likely to say no for someone with those particular settings. And it even tells what factors in this particular customer's case makes them more likely to say yes or no. Their age had a strong influence on the fact that they said no. People of that age normally said no. And then the campaign, the number of times contacting a campaign would go towards that, but it's counterbalanced by these things. So the simulator with explanation here gives very high degree of managerial insight. And this is very useful for making point-by-point estimates and predictions on whether specific customers would say yes or no. So this is a very comprehensive set of information that RapidMiner provides. And we might, if we looked at all these things, although naive Bayes, there's no one model that has the best results on everything, but I like the naive Bayes. It has a high AUC. Its performance is quite good without cheating, making everything 100%, saying everyone said yes. And the lift chart is good. So eventually, we might select this model. Now, to actually deploy a model, that's to take it out of RapidMiner into business operations. Well, there's a whole deploy procedure which is integrated in RapidMiner's server side, but that's not what we're doing here. If you just want to save the results, well, two things you can do. You can save all the results that you got. Actually, I don't have that here because I actually loaded this from a save process. But normally you have a save results option, and then you can save it into RapidMiner, into a repository. So in my case, I've actually saved this in a repository and just saved it in a folder, and that's where I got it from. So when you save it, it's now here. I have auto model, bank marketing, auto model results, and it has detailed folders, results for each aspect, results for each model. And by clicking on auto model results, you can load everything back up again. Okay, so back in auto model, but one useful thing, you can open this process that you like. So I like naive Bayes process, a model, and here auto model gives you the full RapidMiner process. So this gives every step right from the beginning that saves and loads the data, then it takes it to another step. So you can see that RapidMiner does quite a lot through auto model, has a lot of steps. There's optional steps for everything. So this is just for this one naive Bayes model. And it's a full process. You can modify it, and there's a lot of documentation, but you can just run it like any other process. And so I'll just run that naive Bayes process, and it just executes like any other process in RapidMiner to produce those results. So let me just accelerate so that we can see those the results there. So here we have the results of the naive Bayes process. We have the performance vector. Remember the same result that we saw in auto model. You can go back to auto model and you can let's say that's naive Bayes. You can see it's exactly the same results that we got. You have all these different components. You have things like the lift charts that we got. We have, you can really explore around here, but here's some details of exploration of the predictions. Here's a summary of what we got here. So by flipping through this, you can get eventually all the results that you have, but the nice thing is that we can actually modify it. So if there's anything you want to fine tune, like maybe balance the data or add something else, you can do that and you can learn more about how auto model works. And so that's basically how we can do cost-sensitive scoring using RapidMiner's auto model.